Well, I'll start off with the introduction first, and I'd like to welcome you all to our first webinar here in the series. Again, I am Laura Edwards, and I am part of the team that helped organize these webinars. Hans Schmidt is the one managing the webinar software for you today. Also Dennis Todey from South Dakota, Tyler Williams from Nebraska, and Peter Tomlinson from Kansas State. We all wrote the proposal here to get some support to offer this for you today. Our objective here for this webinar series is to increase awareness and capacity, particularly within Extension in the North Central region, to address climate change in agricultural systems. And this is the first of our 6-part series, kind of laying the foundation for climate science and what we know in our region. And so we have 2 speakers today. Jeff Andresen will be speaking first. He is the state climatologist from Michigan State and also associate professor of geography there at Michigan State, and expert on weather and climate, and particularly regarding agriculture and ag production. And so I will let Jeff take it from here. One more thing I'd like to mention is that we do have some kind of questions for you, the participants, to respond to throughout and at the end of the webinar. So please participate in those and give us some feedback both to the presenters and to us as to what you've learned or picked up and might use from these webinars. And so I will leave it at that and look for those questions throughout. And Jeff, you may go ahead. Thank you.
Okay. Thank you, Laura, and good afternoon. As Laura mentioned, is our series here looking at climate and ultimately impacts on agriculture. We're going to start with some basics of climatology, and for the next 15 or 20 minutes, I'm going to talk about global, very large-scale trends and factors and where some of the science is right now, and then I'll hand it over to my colleague, Dr. Dennis Todey in Brookings, who's going to be talking more about the North Central region and more specific. But you will see parallels between both of these. In my talk here, I'm going to begin by talking about climate change and the idea of a dynamic climate. That's one of the take-homes, I think, for today. We'll look at some historical trends, talk a little bit about variability, and then some future projections. But again, here, for our initial discussion, the focus is going to be mostly on the global scale. Well, starting to talk about historical trends and so forth, it's, as I mentioned, one take-home without question is the notion and the idea that while we commonly think of climate as humans as something relatively static and stable, it's anything but. It has changed dramatically in the past, and that undoubtedly will be the case in the future. Here are some examples, and I apologize for the fine print because there's a lot to write about here. But here, these are some taken from the Great Lakes region. These are typical of the upper Midwest, but the climate here, suffice to say, has ranged from tropical 400 million years ago during the Carboniferous and Devonian eras to glacial and everything in between. And so it's a huge, huge change just really in the same region, the same place. The current climate that we have in our region basically dates back about 5,000 years, or at least what we could call something similar to where we are. If you're close enough to your screen, or if you have a large enough screen, the little inset up on the top bullet there, for those of the right, I know we've got a couple people from Michigan that would recognize that, but that's a Petoskey stone, and that is the state rock of Michigan. And it is a rock, but it's a special kind, and it's fossilized coral. And of course, most of you realize that coral takes tropical conditions to survive, and that's the point here. While our region was tropical, that's when these corals grew and ultimately became fossilized. And now, if you walk along the beach in certain parts of the state, you can still find these pieces of a fossilized pieces of a climate of long, long ago. So again, the point here is that there are huge, huge changes in climate to start. There are a number of reasons for those changes that are, well, they're natural. I think we have to call them that. Those range from global plate tectonics, looking at the individual plates that individual continents and other parts of the world or regions are located on. The tropical climate that I mentioned before, 400 million years ago, occurred when the North American plate, which we were all on right now, was much closer to the equator. And so there was much more solar radiation. Climate was much, much warmer. There also are small but still measurable variations in solar intensity. Remember, solar energy is the overwhelmingly primary source of energy driving the Earth's climate system. There also similarly are changes, very small but still detectable changes in the Earth's orbit around the sun that result in an ultimate net change of energy coming into the system. That's something referred to collectively as the Milankovitch theory, and it's the primary theory describing our major glacial and interglacial cycles for the last several million years. We have volcanic eruptions, if they're large enough and can spew volcanic ash and dust up into the stratosphere, high enough into the atmosphere, we can block out incoming solar radiation and have at least temporary cooling. That was the case following the eruption, for example, of Mount Pinatubo in the Philippines back in the early 90s. Another form of that, a much more serious one, is an impact of a meteor, which can also spew up large amounts of dust and ash that block out incoming solar radiation. And finally here we can have periodic changes in the Earth's cycles of carbon and nitrogen, which have a role which I'll get to next, and can be greenhouse gases in our atmosphere. One of the next points here is the realization that the concentration of carbon dioxide and it's very small. It's just a couple hundredths of 1% in the atmosphere. But carbon dioxide is a greenhouse gas, and I think we've all heard a great deal about that. And it's a trace gas in the atmosphere. However, the surface temperature on the Earth is highly, highly correlated with the concentration of CO2. The series that you're looking at right now, currently, it's a little bit, I guess, like Hebrew. We go from right to left, to reading backwards here. But the present is over here in the far right. And it goes back in time, in this case, about 350,000 years ago. And if you're wondering, well, who was the poor meteorological observer who took these data, the red here is surface temperature. These weren't taken by any humans. They were obtained from ice cores in the Antarctic. And well, there's some clever ways of obtaining these types of things, but something called paleoclimatology, or study of paleoclimatology. But the CO2 concentration here depicted in blue, you can see a very, very strong correlation between the two. Sometimes the temperature increases or changes precede those in CO2, and sometimes the reverse is true. That's important to note as well. There are also, besides the number of the natural mechanisms I mentioned, there are also a number of changes or processes associated with human activities that are associated with climate change. And at the top of the list, of course, and what we're going to be talking about here for the next several minutes, are changes in greenhouse gases in our atmosphere. Remember that because the Earth has an atmosphere, it would be, well, it's much warmer than it would be normally in terms of radiative balance, a full 60 degrees warmer than it would be otherwise. And that warming, it's literally like putting an extra blanket on, is the result of several trace atmospheric greenhouse gases. I'll talk about those a little bit. And of course, those have changed over time, sometimes due to natural causes, sometimes, as in the case of the last basically 200 years, a lot of human activity involved. There are other types of gases that are also involved here, ozone being a good example that has a different role in the atmosphere. And finally, one you might not have thought about, but that is land use change related to human activity. And if humans alter the landscape to a sufficient extent, they can change basically the physics of that landscape, absorbing more or relatively less energy than was the case before, and result in a change in climate. Usually the land use changes tend to be more local or regional, not global, whereas the greenhouse gas changes tend to be large-scale or global. So there are a number of mechanisms that are responsible for these changes, of course, what we're concerned with now are the changes since really the Industrial Revolution in the mid-18th century in increasing concentrations of greenhouse gases. Let's look at some temperature trends now. These are observed temperature trends taken from the best observations that we have that we can trust, and essentially those go back to the middle 19th century. And this particular series goes through 2012. But one thing you can see here on the top, these are, again, global average temperatures with both land and ocean surfaces. Remember that 70% of the Earth's surface is covered by water, so this is a big average. You can see a warming of something on the order of 1 degree Celsius has taken place since the beginning of last century up until the present. There was at the very, very end here, the last 10 to 20 years, a little bit of a leveling off. That has since stopped. And I should say before going that 2014 and 2015 now are the warmest years on record. 2015 actually is the new record, and that all 10 warmest years on record have occurred in the last 20 years. So warming globally is pretty hard to refute. There's a great deal of evidence that follows this warming trend. Another point here, if we look down at the bottom here, is that the rates of warming have been different in different parts of the world. So even though we have an average, it's only a global average, and some places have different trends. But overall, if you look at this, areas here with color are areas that there was sufficient data to do a trend analysis between 1901 and 2012. The highest changes, or the highest warming in this case, are in the sort of the reddish purple colors, and you can see that most of those worldwide have occurred in middle and high latitude areas, and that's generally the case. There are a couple of areas, interestingly enough, where we've actually seen some net cooling. One of those, the largest area here, is up in the North Atlantic, south of Greenland. There's also another area in the southeastern U.S. where the long-term temperature trends suggest still a little bit of a decrease. But overall, the vast majority of the world has warmed, especially during the last several decades. In terms of precipitation, a little bit more complex pattern. Here, the color schemes, well, we have two different time frames, 1901 to 2010 on the left, and then the last 60 years here on the right. They're similar, but you can see overall, if we look at this globally, there have been general increases in precipitation in many mid-latitude and high-latitude areas and decreases in lower latitude areas. Here, especially the case over the Mediterranean basin, portions of Africa, portions of Asia. The blues, again, are increases. The browns are decreases. So this one depends greatly on where you are, but in general, there's been increases at high latitudes and vice versa in low latitudes. Some additional trends of note that are associated, especially with the temperature trend, with warmer temperatures, we basically have less ice and snow around the world. The top graph here shows the trend in Northern Hemisphere spring snow cover, and that's been decreasing for about the last 50 years. Here, as you can see, Arctic summer ice extent also declining fairly rapidly over the last couple decades. We could also look at glaciers. The majority of glaciers in the world are receding or melting back, and of course, as a result of melting ice, and also because of thermal expansion, if we look at global average sea level here down at the very bottom, that is on the increase. And so some of these trends are associated already with other direct impacts globally. Some of the greenhouse gases I mentioned, I certainly talked about carbon dioxide. If you're wondering which ones are responsible for some of the changes we see, well, carbon dioxide is the biggest one, somewhere on the order of about 60 to 65% of the radiative forcing that causes the warming, but there are a couple of other ones that are important. Methane, halocarbons, which is, of course, a family of man-made gases, and also nitrous oxides down here, N2O. These, in this particular graph here, graphic, these are portrayed in terms of the radiative forcing related to that gas in the atmosphere, and you can see that most of these here are on the order of maybe a half to 1.5 to maybe even 2 watts per meter squared. And the reason I bring that up is because if we average around the entire world and we look at the radiative balance between the sun and the earth, and then of course the radiation or the energy that it re-emits back out to space, that average, if you average it over the entire world, is about 240. So these changes here that we're looking at that are related to Recent changes in greenhouse gas concentrations are relatively small, but they result in a net increase. You can see that these values here, radiative forcing somewhere between 1 and 2 watts per meter squared more now than we had 250 years ago in the beginning of the Industrial Revolution. So that's essentially the physics. With that extra 2 watts per meter squared, that energy has to go somewhere, and where it goes is warming, especially the lowest part of the atmosphere. Let's look at some future projections given what we've just seen and what's expected to happen. And you might wonder, well, how do we estimate, or how do we project where we're headed? And it's a very, very complicated problem, and atmospheric scientists have been working on this for a number of decades, but the good news is that they have figured out most of the physics, not all of it, but a good deal of it is understood now, and a lot of progress has been made in that. But looking at this is a diagram of all of the different processes that need to be taken into account. The oceans, the atmosphere, the biosphere, the cryosphere, all of these need to be taken into account. They all have a role in Earth's climate, and so this is a very, very complicated issue or challenge. And these relationships are fed into a large computer model, and it's some of the biggest users of computer horsepower around the world, and sometimes they take months to run, but these simulations are run, and basically a number of assumptions have to be made about what the future may hold regarding greenhouse gases and so forth. I'll talk more about those in a second, but there's a very important question, and that is if these projections we get from computer models, if we have any faith in them or any confidence in them, we better be able to simulate what's happened in the past, what we know. And so one of the projects here, and this has been the case over at least the last 10 years, is many of the modeling groups around the world, and there are a few dozen of these groups that run these big models, global models. They go back in time and they say, well, we know, we have observations, here's what happened. What does the model say if we start it with the same conditions and we follow it through time up to the present? And what you see here, this figure, is basically the result of that by continent and also by land surface, ocean surface, and then finally combined land and ocean surface. And so looking here at, let's look at the land and ocean surface on the bottom. This is basically everything. Two model runs are made, and one is made using only natural forcings in the model. That is some of those, the Milankovitch cycle and other cycles that are known about. If you do that, you get the model run here in the blue, and the blue envelope here is taking into account all of the individual scenarios. This has been done, again, repeated in a number of places around the world, and that's the range you get between, this is done approximately between 1900 and the middle of last decade. That would be the blue here. The pink or salmon color here, that is the same run, except now we are adding the influence and impact of greenhouse gases in the atmosphere, and you just saw some of those, what those are, the carbon dioxide, methane, etc., and that those are added to the model, and you can see that there is a difference here, especially over the last half century, and those indicate a warming of the world or the globe as a whole. And finally, the thick black line here, those are the observations taken from our network of observations around the world. And what you can see here overall, in almost all of these cases, is the models using both natural and anthropogenic or man-made forcings are much, much closer to reality than are those with just natural forcings alone. And this basically says a couple things. It says that it's very, very likely or highly likely that human activity has resulted in at least some of the warming of the last century to century and a half. It also, secondly, and just as importantly, it gives scientists a great deal more confidence about what these models are telling us, perhaps for the future. And that's where we're headed next. One of the assumptions is that greenhouse gas concentrations are on the increase. And this particular figure, looking in the future, this is a few years old, but it's still I think representative. And if we look into the future here, there are several different scenarios. These depend on factors such as economic growth, political deals, and collaboration between different countries around the world. There's a number of of non-physical factors that have to play a role here, but technology is a big one, and you can see that depending on which of these individual emission scenarios that we look at, we have a wide range of directions, but almost all of them, the vast majority of these suggest further warming, and that's essentially the theme that you're going to be seeing here for the next couple of minutes. This next graph here is the current schematic showing global temperatures projected here towards the end of the century, and these suggest, all of them suggest warming. There are no exceptions to this. These numbers here are the number of different individual models that were run, so you can see there's very strong agreement, at least in terms of direction, and the higher the warming, the higher the greenhouse gas emissions. That's also another take-home here as well. But again, the range by the end of this century relative to the recent past is 1 to 4 degrees Celsius, so that'd be about 2 to 7 degrees Fahrenheit, and that's the global average. Down here in the lower left, I have the last version. Both of these are taken from the Intergovernmental Panel on Climate Change. The one that we're looking, the larger one here, is the most recent assessment, and the one on the bottom is the one previous to that. But again, a very, very similar theme here with a range of projections depending on emission scenarios. Let's look at some individual changes in temperature and precipitation. Those are the top two panels here. You can see, just like we saw for the trends, not all areas of the world are expected to warm the same. By and large, there's relatively more warming projected at high latitudes of the northern hemisphere, which is where we have the most landmass, and relatively less warming projected for the subtropics, and especially in the southern hemisphere, where most of the surface is water. But the Midwest, the upper Midwest here, the north central region that we can see here is in one of the areas of a little bit larger warming. The two panels here on the left and right are different emission scenarios. The one on the left, it's important to note, is basically a relatively green or a relatively low emission scenario outlook of the future. And you can see the warming is significantly less, while the one on the right is a business as usual, where humans basically don't make any changes. We just continue as we have been, and you can see that the result in that, at least in the simulations, is a much larger amount of warming. For precipitation, it's a little bit more complex. Much of at least the northern part of North America and a lot of the upper Midwest is projected to be a bit wetter on average than has been the case in the past. It's also important, and I think Dennis will talk about this a little bit, but you have to look at the distribution of precipitation. In addition, these are total annual totals. But globally here, what we see, especially as we move to the higher emission scenarios, we see wetter, more precipitation at high latitudes, less precipitation down in the subtropics. And that's a huge deal when we look at global food production systems. There are many people, obviously, in these areas with projected drying, and with warmer temperatures, less precipitation. That's a major, major problem. Now, the bottom two here with warmer temperatures, this is a no-brainer. We would expect to see less ice than we have. That's what the third panel is here. And then finally, with increasing temperatures and with more carbon dioxide in the atmosphere, we would also expect to see a little bit of a drop in pH, or a more acidic ocean than has been the case in the past. One other one here related to precipitation. With higher temperatures, it's also important to look at factors like evaporation and relative humidity. For relative humidity, for example, for much of the lower 48 or the continental U.S. here, you can see a decrease in relative humidity. Much of that is due to the increase in temperature. Remember, relative humidity depends on both air temperature and humidity levels. It also suggests, because of the warming and, the warming temperatures and lack of water, that soil moisture on average might decline. And that's true over much of the mid-latitudes and some of the tropical latitudes around the world. You can see much of Europe, parts of Russia, a lot of North America, a lot of South America. Average soil moisture is projected to decline. It's before we end here, one important take-home, and it's one we really can't overemphasize enough, and that is that mean changes are one thing, and it's we've looked at basic mean state changes in climatic variables such as temperature and precipitation, but we also have to consider the variability of those variables. Extreme events would be at the top of this list here. There are a number of reasons for this, but as you can see, the wording here, our own human history suggests that humans have been actually fairly good about adapting or changing or being able to adapt to long-term steady-state changes in temperature or precipitation. But when you change the variability, you change, for example, the incidence of extreme events such as droughts, severe storms, that's a much more difficult thing to deal with. And I would say at this point it's also important to note that this topic, and it's even though extreme events are rare, they account for a large fraction of the impacts on human systems. That certainly includes agriculture. Unfortunately, it's one of the issues, one of the pieces of the puzzle that less is known about, because the model projections that we have for the future just don't do very well with this, and it's a real research need. It's one that more science is needed. A couple of examples. Here's one from locally here for me, or from Michigan. In terms of extreme events, we had an unprecedented heat wave at the beginning of the spring season back in March 2012. Of course, that was followed by a series of freezes that wiped out our fruit crop. It was also followed by one of the largest droughts in over 20 years, since 1988, across much of the Midwest, including Michigan. And ironically, that was followed by the wettest year on record in Michigan in 2013. We've had two terrible winters before this year, with 2013, 2014 being one for the record books. And flip-flop that, we had the warmest December on record here in 2015. So lots of extremes here in the recent past. And one comment on that, another I think take-home factor. There are a couple of graphs here. The large one here is the number of worldwide billion-dollar-plus weather disasters from 1980 through 2010. That's down here with the large bars, and you can see the orange ones are losses, overall losses. The blue part of the bar is the amount of loss that's insured, which is a little sobering. You look at a lot of these, and most of it you can see was not insured. Remember, these are globally. These are all around the world. And we have taken inflation into account. They're actually, the lower graph here, it's all in terms of 2010 dollars. But you can see without question that the number of these events has been on the increase. Here's 2005. That, of course, is related to all of the hurricanes that occurred that year. That one is still the record. And then for comparison, I put here on the top as an inset, this is a new one, or a newer one. These are billion-dollar disasters in the U.S., and you can see that the trend is also upward. And for the U.S., if you look at the causal factors here for the U.S., many of them are due to severe storms. Hurricanes are another big one. Flooding would be a third one, and droughts, of course, are also here. On the international scale, the majority of these are due to tropical cyclones or hurricanes and droughts. Those are the two biggest one. But the interesting part here is it's not the end of the story, and that is that some of these types of events, depending on we see more flooding or rain events, that is one increase. But some of these are not increasing over time. Hurricanes would be one example of that in the Atlantic Basin. They're not as high, the number now, as they have been in the past. And so one looks at these graphs and say, well, how is that possible? And of course the only other answer is that we as humans have more of our stuff that's in the way, and that's, I guess, a scientific way of saying we're becoming more vulnerable with time. So that's one to think about here. The vulnerability of us as humans is likely changing, and that's probably it's resulting in at least some of the increase that you see here. Here's another example of an extreme event. This is a projection of droughts around the world here, looking out towards the end of the century. This is a very recent study, but you can see that in some parts of the world, given the high emission scenario is on the bottom, a moderate emission scenario in the middle, and then the low emission scenario on the top. But what this study concluded here is there are some parts of the world, notably lots of South America, parts of Central America, South Africa, the Mediterranean Basin, and Australia, where the incidence and occurrence of drought in the future, especially severe drought, is expected to increase. And of course, that is not a positive thing. So moving on here and trying to summarize, and I'll hand it off to Dennis. The Earth, the world is becoming warmer, and it's not in every single location in the world, but the vast majority of the world has warmed, especially over the last half century. Relatively more warming across middle and high latitude areas, and that warming has resulted in melting of a lot of ice as well as an increase in sea level. Precipitation is a little bit more complicated, but in general, increases in middle and high latitude areas and the reverse in low latitudes. And looking into the future, assuming greater certainly concentrations or continued emissions of greenhouse gases, more warming is projected, and the range of that warming, depending on the emission scenario, is somewhere on the order of 2 to 7 degrees Fahrenheit by the end of this century. And like was true for the observed warming, and it may be coincidence, but relatively more warming is projected in middle and high latitudes, relatively less in low latitudes, and especially in the southern hemisphere. And as we've just seen, again, we can't emphasize this enough, that changing climate is a challenge enough, but variability is a huge piece of this, and more is needed, or more science is needed on this one. But it's a key wild card in this process. And with that, I'll finish up and hand off. Thank you.
Great, thank you, Jeff. As we transition over to Dennis's presentation, are there any questions from the audience? You can type them into the chat box. So I will introduce Dennis here. He is the state climatologist for South Dakota, our Extension state climatologist based out of Brookings, and he has been there for over a decade in the role of state climatologist in Brookings, and I believe he's coming to us today actually from Washington, D.C. area. And Dennis, I'll let you take it from here.
Okay. Thanks for the introduction, Laura. You are correct. I'm in the D.C. area. Actually, I'm in Crystal City, Virginia, at a meeting. The wonders of technology are great, where you can be presenting remotely from a remote site. So to be a little more precise, I've been at SDSU just over 13 years, just had my 13-year anniversary. They haven't given me a 13-year pin. I think that's bad luck or something like that for having a 13-year pin. Great lead off there, Jeff, giving us some global scale looks at climate and some of the climate drivers. We're going to zero in a little bit more now on some of the observed changes and give you a couple of websites where you can go look at information for your locality. Just a couple things to bring this down. Jeff gave you a larger picture at what our climate is changing like, but to give you a little more precise version of it, when we use climate averages, we use 30-year averages as the comparison when we're always comparing to average. So here's the 30-year normal or 30-year average annual precipitation for the whole U.S. using PRISM data that shows, an overall distribution of what we have in the way of precipitation, ranging from the 40-plus inch range in the southern part of the Corn Belt area up to our area in the western Dakotas, where you're dealing with, down to 12 to 14 inches of precipitation, and a very strong gradient here across the Dakotas presents some interesting challenges in that region. From a temperature standpoint, temperature is much more well-behaved. I guess let's go back up to precipitation. Here you see the influence of the Gulf of Mexico. Moisture from the Gulf of Mexico is able to be transported and drop precipitation. Too much precipitation, as we saw in the December rainfall totals in the southern part of the Corn Belt, Missouri, Illinois, and Iowa. But temperature is much more latitudinally based, along with the distribution of solar radiation and sunlight. Further south areas are generally warmer, further north areas are generally colder. Small variations in that based on snow cover and some other issues, but generally more latitudinally based. So let's look at some of the changes that we're experiencing overall, and we're talking more on a near-term basis from the measured period. Jeff gave you some perspectives on where we're using some of the proxy data. Now we're looking at some of the measured changes. And the changes that we're talking about are more complex. Not to try to confuse the issue, but it's, the global warming term, assume, well, everybody's getting warmer. Well, it's much more complex than just warming. There are large precipitation changes, and in some of our region, that is the bigger driver in some of the issues we've seen recently than temperature changes are. And we'll talk more about that as we go along. Changes in time of year of precipitation, particularly, we'll talk about. Temperature-wise, max-min differences. There's some differences in high temperatures versus low temperatures throughout the year, and certainly some locational differences. In this shorter time period, we won't be able to cover them all, but we'll give you a flavor of them where you can go to find out more information. Now, our first slides here are derived from what's called the National Climate Assessment. It is a congressionally mandated report that is supposed to come out every 5 years. The last one was delayed a little bit. Basically, the assessment is what is going on with climate in the country. How is it changing? What are the impacts we're having because of it? And that's also a new area of address, is not only how is climate changing, but what are the impacts we're having because of that? Lots of times negative. Sometimes there are positive changes that have, because of the way the climate is going, and tracking some of those. So our first one is observed U.S. temperature changes over the last century, basically since about 1900 till the present. The redder the area is, the more the temperature has changed. The reddest areas have increased by more than 1.5 degrees, and this is Fahrenheit. And Jeff kind of got at this with a global view. Some areas in the south central part of the U.S. Our changes over the last century have been slightly cooler. Up into the Corn Belt, somewhat lesser changes, more of like Jeff talked about, the northern areas, the further north you are, the more warming we have seen in this region. And if you track what's happening with corn production in the area, there's you can see kind of a driver related to that, with more warming being able to move corn north. Certainly there have been varietal changes, but climate is also being a driver related to this. The graphs around show the decadal changes for the different regions across the country, giving you an idea of which ones have been warmer, which ones have been colder. From a precipitation side, over the same time period, how much precipitation is changing? This is based on percent. The greener areas are over 15% increase in precipitation over the last century. Browner areas are decreases in precipitation. And then again, the areas are broken down by decade in some of these subgraphs. So you see that the north central region is ground zero for some of the biggest precipitation changes we have seen over our region. I mentioned this, some of the bigger drivers. Certainly in the Dakotas over the last 2 to 3 decades, there have been big changes in what has happened with water, timing of water, and has greatly impacted crop production and crop management. Not to be left out, other parts of the Corn Belt are also seeing some of those increases in precipitation, not quite as much in some places, but we are seeing overall increases. One that I would just like to point out from a national scale is just Arizona, and you think about the number of people that have moved to Arizona in the last 50 years and what is happening in precipitation. If you're taking it desert, you're making it drier, so it's really changing our situation. Certainly also the increase in precipitation is also having an effect on crops. Our areas of the north that have typically been small grains are now leading to enough precipitation where you can convert some of those small grains to more row crops, growing more corn and soybeans because they get enough precipitation. A big indicator of that is western South Dakota, west of the river, where corn has not been grown, and it is being grown more because of some overall increases in precipitation. Part of the problem with precipitation, though, is not as overall increases, but those increases occurring in bigger rainfall events. This is a way of talking with producers about this, and most of them recognize this. And when we're talking about what's going on with climate, is understanding that there are changes in big rainfall events. We're getting more big rainfall events at different times of the year, and that is leading to problems with crop production and particularly soils, soil management. There are some places I have seen with people who like to do tillage where they've had several inch rainfall events that are occurring on tilled ground, and we're losing a lot of soil in this situation. So bigger rainfall events that have produced a number of larger issues. Because of bigger rainfall events, we're also seeing increases in flooding. This is a study by the USGS. Basically, the greener areas, more big changes in flooding. Browner areas seeing less flooding, and the larger the scale. So just more flooding occurring in lots of places in the north central region. To zoom in a little bit more, this is a website you might want to take down, or it'll be in the recordings. because if you want to get a look at your state or even your region, you can break down certain parts of states by climate divisions where the data has been averaged either over the state or over the climate division to be able to show what is happening in the way of temperatures and precipitation or some of the drought severity indices. You can take this back to about 121 years of data now, and you can see a lot of the variability and trends over time. So we're going to show you some of these for South Dakota as an example. I didn't want to inundate you with a bunch of these, but South Dakota indicates some of the overall trends. Here's the change in overall precipitation for South Dakota over the time period I showed before, where we've seen an increase from about 18 inches statewide average to around 20 inches, and this corresponds with about that 15% increase, just a little less than 15% increase over the 120-year period. Certainly you see a lot of the variability involved. Dust Bowl years here, and the more wet years we have seen over the last 20 to 30 years that we have indicated. We still have those major droughts. Jeff indicated the 2012 drought right here. 2006 and 2002 droughts still do occur, even though compared to the Dust Bowl, they are individual years compared to the whole Dust Bowl. Let's break this down by seasons now. We're looking at the four plots you see here are seasonal precipitation. Upper left is spring, which we consider March, April, May, climatological spring. The upper right is summer. The lower left is fall, September through November, and then the winter is December through February. These vary somewhat by where you are across the region, but there are some commonalities across the region. If you look at the trend line, again, it's very difficult to address trend lines with such highly variable ones, but it gives you an idea that South Dakota precipitation is increasing in spring and particularly in fall. And if you look at the eastern Dakotas and into Minnesota, this fall precipitation trend has been incredibly large. But the common thing across the whole region is these transition seasons are where we're seeing our bigger increases in the precipitation amounts. For those of you who deal with agriculture, and if you talk to most producers and say, do you want more rainfall in the spring and fall or in the middle of summer, they're going to say they want more in the middle of summer when the crop is using it. That makes the most sense. But if you look at what has happened in our summer trends are relatively flat. When you look, they vary a little bit, but more of our precipitation increases are occurring in our transition seasons. And actually in South Dakota, our winter is seeing some slight decreases despite some high variabilities. But it's these transition seasons, and especially there's some changes in our extreme precipitation events are occurring in transition seasons, which present some real problems for us. From the temperature side, if we break down the temperature, this is just December through February, so winter temperature. More of our warming is occurring in winter. And the other piece along this that's very interesting with comparing what's happening in the way of temperatures is the differences between max temperature, the high temperatures averaged out over a season, and the low temperatures averaged out over a season. Here's South Dakota with splitting out summertime highs on the top left and summertime lows on the lower right-hand side. You see the summertime highs, the trend is maybe slightly upward, but statistically it would not be significant. But if we look at the minimum temperatures, and this is very common throughout most seasons and all across the north central U.S., is that most of the warming we're seeing is from overnight lows and less so from the daytime highs, especially during the warm season. So that we are getting warmer in the summer, but it's being driven by low temperatures and not so much on the high temperature side. A couple other changes that we're seeing commonly across the region are increases in dew point. Dew point is an absolute measure of amount of moisture in the air. That's not quite the definition of what the dew point is, but basically the higher the dew point, the more moisture there is in the air, and that is highly variable but increasing over time. And this has been reported by several authors, increases in dew points throughout the year, particularly high dew point episode, extreme dew point episodes, which has impetus or problems on livestock, where it becomes stressful for livestock, and also people who are not in air-conditioned housing. So a very more common issue that we have seen. This has sometimes been related to corn production. I don't think that's quite all the case. The other overall trend we've seen is the increased frost, or the increase in frost-free season. Last spring, average spring freeze getting earlier. First fall freeze getting later, so we're seeing an increase of that frost-free period, so again allows more of that corn production to move further north. An interesting feature, though, I was talking with folks in Nebraska is, can we relate this situation where we're getting an increase in the earlier spring last freeze, but if you're getting wetter in the spring, can you get out and take advantage of that time period? It's an interesting question, something we haven't tried to address well over yet. That's one other thing. This was kind of hard to compare, but if you compare plant hardiness zones in the last map in 1990, the blue areas here are zone 4, zone 5 down in this region, southern part of the north central region. How that has changed is we've seen a northward movement in the plant hardiness zones. Zone 4 has moved further north, zone 5 has moved further north. So from a horticulture standpoint, you see, chances to move certain horticultural crops to different areas. Okay, kind of wrapping this up. Jeff showed you the look ahead. What's overall from a local standpoint and a near-term standpoint. There's really no reason to see these overall trends change. There are going to be these continued variabilities. We will have droughts. We will have heavy rainfall events, but the overall changes we expect to see going ahead, year-to-year variability will increase, possibly increasing variability. Certainly that's a risk issue, and Jeff did a good job of addressing that. I was at a meeting in the Twin Cities a couple of years ago, and there was a person there from the insurance industry, and he said the insurance industry doesn't have to be convinced that there's something going on because they've seen their payouts increasing exponentially because of large losses because of various weather events. There needs to be more regional climate modeling because of the regional scale of precipitation issues. There's been some discrepancies as to whether we're going to get more rainfall or less rainfall. I think some more regional modeling needs to be done to deal with some of these issues. So that's the end of my presentation. Jeff, you can kibitz in there and any other pieces from your side, or we can go to questions from those in attendance.
Great, thanks, Dennis. There is a question in the Q&A box, if you and Jeff see that, from Eugene.
Trying to pull it up on my here.
I see it.
Okay.
Okay, so I'll have to ask if I'm interpreting this correctly. But are the global models mostly calculated information, or are they reliant on calibration with recent changes in climate? This is a complicated question, but in general, these models are based on the equations of motion and conservation of energy and water, etc. There is some calibration involved in them, but by and large, they're independent physical relationships put into mathematical form. So I would say most of this is basically calculated or estimated with those equations. Dennis, any thoughts on that?
You're the modeler. I'll let you swing that. I'll take the easy one from Eugene down below with the Global Climate Conference. Does it mean to reducing global warming? The proof is really in the pudding about will countries stick to their commitments. It was specifically structured that there did not have to be required commitments because basically the U.S. negotiators knew that that was dead on arrival coming back. They could never get that through Congress. So what they're trying to do is make these commitments toward reducing greenhouse gases, and then try to have people meet regularly and show how they're meeting targets, and then try to hold each other responsible is what our goal with that is. And I say our goal with the negotiators, and that's that's why there have been the president has taken some of these steps to try to make commitments to reduce greenhouse gas emissions. It's not simple. It is far from simple, and you're trying to get a lot of players to commit to this. So we'll see how well this sticks with us here.
And one follow-up on that, I agree completely. This is obviously it's a global issue. There's a great deal of evidence that is pointing in one direction, and it's a real threat, at least in my opinion. But it will require unprecedented international cooperation, as Dennis has described, and this politically is a very, very complicated thing to do. But that said, we can look back over 30 years ago, an international agreement called the Montreal Protocol, which was basically put in effect to address the issue of declining ozone concentrations. And ozone, I won't go on with the nicknames, and we'll talk about those, but ozone has a very, very critically important role in the atmosphere, and that is that it blocks out some high energy forms of radiation in the atmosphere. If it weren't there, and those we're talking about X-ray and gamma ray radiation from the sun, there would be no life on the planet. So the ozone plays a critical role, and if it's not there, of course, more of that dangerous radiation gets down to the surface. And scientists realized that several decades ago, and the fact that it was man-made gases, primarily the chlorofluorocarbons, the CFCs, that were responsible for this decline in ozone. And at that time, an agreement was signed, and it was put into effect, and it was enforceable. And the bottom line is it generally worked. And if we look back now in time, we actually are looking now at projections of the ozone declines are really not occurring anymore, and expected to recover because of that agreement. So we know how difficult it is politically to get anybody in agreement with anything, but you can point at that and say it has worked in the past. It is possible.
All right, thanks, Jeff. Before we get to the next question, I'd like to remind folks that there's a poll question down there on your screen, and then we ask that you please respond to that in the next minute or two, as we have a couple other poll questions also that will follow. All right, I see a couple more questions in the Q&A. Dennis, there's one for you regarding the summer prediction.
Putting me on the spot. The new outlooks will be coming out on Thursday. The computer models are hinting at continued warmth even through the summer. It's an odd configuration, but they're hinting at staying warmer than average even through the summer, which would end up putting more water demand on issues. The question is what happens with precipitation, and right now we don't have good indications on overall precipitation, but the warmth could be sticking with us through the spring and summer, so we'd have a little bit longer growing season.
Mm-hmm. All right, thanks, Dennis. And let's see. Oh, and another question there, is there any talk of trying carbon trading again in the U.S.? I'll leave that to both Jeff or Dennis.
I know that it's in the background, and Dennis, you may know more than I do. It's certainly still there, but some of the science is not quite there to understand what economic value the carbon has. I think there's some new technology that's needed, or some new science that's needed to understand that. But I haven't heard anything recently to suggest that we are close to anything like that. It's still there, but nothing soon. Hey, Dennis, have you heard anything more than that?
No, not specifically. I mean, it still exists. It's just that the value of the carbon credits is very small. If any of these agreements start to stick, it will probably come back. But at this point, no, it's really not anywhere in the discussion phase.
Okay, and thank you, Dennis and Jeff. I'd like to remind folks that there are some new poll questions there at the bottom of the screen. If you'd like to respond to those, we'd appreciate that. While you're doing that, I'd like to mention that our next webinar in the series is scheduled for February 18th from 10 to 11 Central Time. And there will be a new link for that one as a separate webinar, so we will distribute that through the same channels that we did for this one, and maybe you'll see it some other ways as well. and we'll give you a couple more minutes. If Dennis, Jeff have a quick thought here in the next minute or so to mention at the end.
I guess as a wrap up, Laura, it's clear that there are some things going on, and this is an avenue you can use if you're concerned about talking with producers. It's an avenue to get them talking about what they're recognizing happening, and survey results are pretty clearly indicating that producers buy into the idea generally that there's something going on. Causes of it are still in their minds up for discussion, but from encouraging them to think about how they manage, this is an avenue you can start entering discussions with them about.
Okay. All right, thanks, Dennis. I think as far as our next webinar, I forgot to mention that would be presented by Jean Tackley from Iowa State University, who will get further into the climate impacts on ag and water management in our region. So we hope you'll tune in for that. At this time, it's just 2 o'clock, and so I'd like to close the webinar. Thank you all for attending, and we look forward to seeing you on another one. Have a great day.